Okay, let's begin. So we have been discussing part-of-speech tagging, which is a form of sequence-to-sequence labeling. Okay, and that's a very general framework. Sequence-to-sequence labeling is a very general framework. It comes in many machine learning situations, and that's why we are spending some time on part-of-speech tagging. It's a very simple, easy to understand problem, but has it's the same technique is applied to so many different situations in machine learning. All right. So today we would like to look at what is called discriminative POS tagging as we move forward. Before that, let's have a one-slide recap uh, for the last week, the week of 12th August. So there we had this interesting discussion on should I apply Bayes rule or not? Okay, in making some classification decision. So one of the situations was cancer detection. So given the patient's features, patient's various parameters, you want to decide whether the patient has cancer or not. So if we apply Bayes theorem, then the probability values we have to consider is the prior probability of the prior probability of cancer. Okay, the prior probability of cancer and the probability of the patient parameters given that the patient has cancer. So these would be the two parameters. Otherwise, if we do not apply Bayes theorem, then we'll have to decide, given the patient parameters, does the patient have cancer or not? Okay. So, so this is how we would like to consider the formulation of the problem. The other problem was the visa granting problem. The visa granting problem is given the application and different properties of the application, like income, for example, age, history of traveling, and so on. Based on this, we have to decide whether the application can be granted visa or not. Okay, these are two different situations. And the question that I asked from you is, should we apply Bayes theorem or not? So this was one nice discussion we had, and that is like a very fundamental point of machine learning situations. The next point was that we illustrated the application of Viterbi algorithm for doing inferencing with respect to part-of-speech tagging. So when we do part-of-speech tagging, we have to produce labels on the sequence of words. And there, we had this very simple sentence of only two words, people laugh. Both people and laugh can be noun and verb. And we discussed if people laugh can be efficiently give a part-of-speech tag. And that we understood is possible through what is called the Viterbi algorithm. You draw the trellis on the sequence of words, and from that sequence of columns of part-of-speech tags, you find out the best possible path giving rise to the best possible tag sequence. Now, one important question was, so the potentially the space of part-of-speech tags is exponential in the length of the input. How come the Viterbi algorithm becomes linear? Okay, linear in the length of the input. So that happens because of pruning of paths. Okay, so when we have people laugh, then various paths which are possible at the first stage, the two partial paths are noun and verb, because people can be both noun and verb. Okay. On the other hand, if we going further from noun, if we produce noun and verb again, looking at laugh, and from the verb, so we have paths which end in the same state. Okay, and out of those paths, only one path is retained. So that is the pruning of paths. Now, pruning of paths actually is responsible for the linear time algorithm. For every word, we maintain only t paths. Okay, T possible paths. So where T is the number of tags in the tag sequence. So for every word, we may maintain T possible paths, and we have to choose the best amongst those T paths. So it makes T to N, where N is the number of words. So the complexity is linear in N. Okay. Then the next point we took up is what is large about large language models? Okay, why are large language models called large? So they're called large because large sequence, the probability of large sequences, which is actually long sequences, that is considered, and that is the that is the main idea behind large language models. So we take very long sequence and compute the probability. Okay, so this probability is the is used for decision making, and this is at the heart of large language models. And then we mentioned that there are three tasks which are solved by hidden Markov model: Viterbi, forward, backward, and Baum-Welch. Okay, so Viterbi algorithm is for finding the best possible state sequence. Forward, backward is for finding the probability of the observation sequence, and Baum-Welch is for finding the transition and observation probabilities for the machine from the data. Okay, so this is what was mainly discussed in the last week. And whenever I present this one slide recap of what was done in the previous week, I'm also inviting you for any kind of questions and comments that you might have. Okay, you are always welcome to stop me and ask any questions. Right. So let's proceed. We would like to today discuss discriminative POS tagging. Now, discriminative generative dichotomy is again basic to machine learning. Should I apply discriminative modeling or generative modeling? So what do you mean by that? We are doing part-of-speech tagging, which in the NLP layer comes above morphology. Morphology deals with the processing of words. Okay. And the reason why part-of-speech tagging is above morphology is because morphological signal, okay, can be made use of for disambiguating tags. So at every word, the correct tag for the word. And that we have seen is actually a disambiguation or search process. Multiple options, you have to choose one. Okay. I know people can be both noun and verb. You have to choose one of the two tags given people. Here, if we know the properties of the word, okay, that the word has a li at the end as a suffix, then most probably the word is an adverb. If there is an ed at the end, then most probably it is a past tense verb. Okay. If there is this unga suffix, unga, for example, then the word is most likely to be a verb. Okay, and so on. So that's why part-of-speech tagging layer is above morphology. And morphological signals can be very helpful for disambiguating part-of-speech tagging. But the scheme that we have seen for part-of-speech tagging, where the task is to produce a part-of-speech tag sequence of words, the input is a raw sequence of words, who is the Prime Minister of India. Then the output is who underscore WP. WP is a relative pronoun. Is underscore VZ. VZ is auxiliary verb. The is a determiner, DET. Then prime is an adjective, JJ. Minister is a noun, NN. Of is a preposition, IN. India is a proper noun, NNP. And question mark is punk, which means punctuation. Okay, so this is the part-of-speech tag which needs to be produced given the raw sequence of words. So the point is that in the way we have learned how to do part-of-speech tagging is through generative modeling. So we take the sequence of words W. And we are interested in the conditional probability of T given W. And it's an argmax computation over all possible T, which immediately makes it a search problem. Okay. The word can have multiple parts of speech. Out of that, you have to choose one. And therefore, T star is argmax of T, probability of T given W. If we apply Bayes' theorem, then we have entered the generative framework for solving this problem. So probability of T into probability of W given T. Probability of W given T is the conditional probability, also called likelihood. Probability of T is the prior probability. So PT gives rise to product of transition probabilities. And probability of W given T gives rise to probability of W given the tag at a sequence. So this is also called lexical or observational probabilities. So ultimately, we deal with product of tags and conditional probability of W word given the tag. This is the product we deal with, okay? And we do it for every possible word position. So this is a generative modeling. Can we do something else? Can the modeling be something else? So that modeling is called discriminative modeling. Okay. So modeling in the discriminative part of speech tagging framework. So the way it is done is that T star is argmax over all possible T, probability of T given W. Okay. So this is the basic formulation. Then the next step is that probability of T given W is marginalized with another random variable called F. Okay. So F is the feature vector corresponding to W. We're given the word sequence. We are interested in a feature vector. The feature vector of what? Feature vector of the whole word sequence, or what? Now, feature, we typically do not look at the whole word sequence. We have a window, and we would like to say that the feature vector is with respect to a particular position. Okay. So if we have a sentence with words W0, W1 up to Wn, then at the ith position, I have to decide on the tag at the ith position. So now you will have to shift your attention from the words to position. Okay. So you have an input sequence, and at every position, there is a word. The words have features, and also the neighboring words have features. Okay. So this can be very nicely abstracted as a feature vector corresponding to a position. So at every position, there is a feature vector. The word in that position is also one of the features. Okay. So that's a different way of looking at the problem. At every position, we have features. One of the features can be the word itself. Okay. Then another feature could be the suffix of the word. Another feature could be the semantic property of the word. If the word happens to be tiger in that position, then the semantic property is that it is a living entity. It's a carnivorous animal and so on. Okay. So this is how the feature is introduced. So now look at the application of probability. Sigma f, probability of T comma f given W. Okay. In a subsequent slide, we clarify what the assumptions are. So now this formulation is very different from what we saw. There is a generative modeling. Probability of T into probability of W given T. This is very different. So what is happening here is that we ultimately have the probability of T given W is estimated as probability of T given F, the feature vector. Actually, it will be a tensor, right? It will be a vector of vectors. So at every position, we have a feature vector. And if the feature vectors are collected, then it will be a vector of vectors. All right. So probability of T given W is probability of T given F. And this becomes probability of Ti given Fi with a product varying from 0 to the length of the input. Okay. So the final final formula is probability of Ti given Fi with product over all possible I. Okay. Now you see the problem has a very different look. It's a product of probabilities, okay, with every position having a feature. The word can be a feature. So this is more general. Earlier, in the earlier formulation, when we did WUNT, we were not breaking the words into its parts. Okay, so that facility was not available in the formulation. In this formulation, which is very, very general, we are working with a feature vector at every position. So this is called discriminative modeling, because at every position, a set of features is discriminating amongst all possible tags, which could have been right there. Okay, so a set of features is aggregated to decide what the tag at that position should be. That's why it is called discriminative modeling. Okay, more details are coming. So this is a different way of solving the problem. Now, what is the motivation? Why should we do discriminative part of speech tagging? There are a number of reasons. So NLP is of course dominated by English, okay? Because a huge amount of resources have been built for English, and English somehow has the advantage of a systematic progress in the field. Okay, there were tools and resources created for words. Then from the words we move to phrases, from phrases to whole sentences, then paragraphs and so on. So at every stage, there were some, I would say, wise people who knew what exactly was needed at that point of time. And all these gradually accumulated and the field really flourished. But the English centric view of NLP is not the whole reality. Okay, there are languages which are extremely different from English in their character. For example, in Indian languages, we know that the verb is sent to the end of the sentence. In English, the verb sits in the middle. Okay, now I invite all of you to think about why some languages choose to send the verb to the end. Okay, why is it that noun phrases are all finished and then comes the verb? Ram ne sham ko dekha. But in English, Ram saw Sham. So the verb coming in the middle, the action is specified early in the sentence. But in Indian languages and many other languages, we have to wait till the end to know what action happened. Okay. Okay. So the verb is yet to come. Ram ne dekha Sham ko. But if you say Ram ne dekha, then the expectation is kisko dekha. Right? Whom did he see? Did he see? So there is expectation built for different entities. Okay, so that's okay. So cannot handle three-word order and agglutination well. I'll give some example. So if adjective after noun is equally likely as adjective before noun, the transition probability is no better than uniform probability, which has high entropy and is uninformative. Okay, so if you consider three-word order languages, where the words can move around. So Ram ne Sham ko dekha is equally good with Sham ko Ram ne dekha. You can get the meaning from this. And that is because of the suffixes ko and ne. They tell us very clearly who is seeing whom. Particularly in the English sentence, Ram saw Sham. So who saw whom? Ram saw Sham. So Ram is the seer, the agent of seeing, and Sham is the object of seeing. Where is that information encoded? position. So that information is encoded in the position. The noun coming before the verb is the agent. The noun coming after the verb is the object. Okay, that's how English encodes the information. This information of who is doing what is called semantic role leveling. So when you can take liberty with the position of words, the positional information can no longer provide you disambiguation information. But somewhere the information has to be there. Okay, somewhere the information has to be there. So that information is in the suffix of the word. Ram ne indicates Ram is the seer. Sham ko indicates who is seeing. Now I'm told that Chinese is a language which can be both free word order and it can also drop suffixes. Chinese is a morphologically poor language. There are not many suffixes in Chinese. And on top of that, you can also take liberty with the position. So then disambiguating Chinese must be a really complex task. Okay, so the position is no longer a helpful clue, and therefore we really cannot work with the transition probabilities effectively. And when the words are long strings of many morphemes, the pause tagging without morphological feature is highly inaccurate. What do I mean by these two problems? Here is some example. Variability in word order, problem for generative model. So in this case, if you look at the sentences, here, look at this sentence. Bharat संघ स्थायी शांति चाहते हैं नए पीएम शहबाज शरीफ. So Bharat Sangh स्थायी शांति चाहते हैं has come in the middle. This is not characteristic of Hindi. Okay, so in the in headlines you often see that the verbs comes in the middle, and most languages follow that kind of practice. Okay, next time you look at Hindi newspaper, Tamil newspaper, Bengali newspaper, you will see in most of the headlines the verb, like English, sits in the middle. Okay, so here there is a free word order happening, and so therefore part of speech tagging of headlines in newspapers will have to tackle this problem of free word order. And agglutination is the problem of many morphemes coming together to form a word. So this is a Finnish word. Okay? I will not attempt to pronounce this word, but it has many important parts. So this whole string means I wonder if I should sit down for a while. And in this whole string, the main entity is ist, which is the verb sit. This is the stem. And then ahta, this is the verb derivation morpheme to do something for a while. So ahta, okay, is the indicator of doing something for a while. ISI is called the conditional affix. If I should sit. Then N is the first person singular suffix, the N at the end that you see. Okay. Then ko is the question particle. Han is a particle for things like reminder or softening with questions and imperatives. So I wonder if I should sit down for a while. This whole thing is captured by one Finnish word. This is the word. What is the part of speech tag of this word? What is the part of speech? It is actually a complete sentence. Okay, so what will make sense is dividing this whole string into small parts, which are all called morphemes, and get their category, and then do useful NLP tasks after that. So is it clear to you? Now we have to change the free word order and agglutination. Agglutination comes from the word glue, stitching things together or sticking things together. Okay, so lots of morphemes are coming together to form this sentence. So there are examples in Indian languages also of agglutination. My favorite example is from Marathi, which is Ghara Samorchiani, Ghar ke samne wale ne. Hindi is not agglutinated. Ghar ke samne wale ne, all of them are separate. But Ghara Samorchiani is together. Tamil has lots of such behavior. Malayalam has this behavior. Manipuri has this behavior. Okay, so their part of speech tagging is not a simple task. An English-centric approach to part of speech tagging will not work there. So this is an example from Manipuri, which is from Northeast. Okay, and the meaning of this is, I wish I myself would have paused to bring in the article. This is a very famous example. My collaborators from Manipur tell me this is the example they typically show to illustrate concepts in NLP for Manipuri language. Okay, Manipuri belongs to what is called the Tibeto-Burman family, and this has a lot of agglutination of this kind. So again, what is the part of speech tag of this whole string? Cannot be decided. Okay, you have to break it up into small parts. Okay, now do all these discussions have some utility? Yes, try to create a large language model for Manipuri or Finnish. Try to create a chatbot for Manipuri Finnish. Try to create a machine translation system for these languages. You'll have to solve this problem. Now let's come to the discriminative modeling, which is probabilistic. So we have T star equal to argmax T, probability of T given W, our starting formulation. Now, probability of T given W is marginalized over all possible feature vectors of feature vectors. Probability of T comma F given W. Now, probability of summation of probability of T comma F given W can be written as probability of T comma F given W, dropping the summation. Okay. Why is it so? The summation dropped because given word and feature engineering, F is unique. Okay. So given the words, and once you have decided what features you will work with, there is no ambiguity with respect to the feature vector at each position. Okay. So therefore, you will get a you will get a unique vector of feature vectors, and therefore summation doesn't make any sense. It will be only one feature vector for the word. Then we apply the Bayes theorem on this. Probability of F given W into probability of T given F comma W. The next step. Okay. So here, probability of F given W, the feature vector given the word sequence is completely determined. Okay. So that's why that probability is 1. And we have probability of T given F comma W. We say that we'll absorb words and their properties in the feature vector F itself. So then I can drop W because it is already accounted for in F. So then we have probability of T given F. So from probability of T given W, we have come to probability of T given F. Okay. And probability of T given F is then expressed as probability of Ti given Fi, I going over all the positions in the sequence. So this is the model. Okay. And this product comes because we are applying Markov independence assumption. This is the formulation. So this is a very nice formulation because we are observing all the features given the word sequence, and from the features we are trying to decide on the part of tag sequence. Okay. So let's take the running example. Hat means start of the sentence. Had brown foxes jumped over the fence, dot. Okay, so the two guardrails are very important for the sentence. The beginning of the sentence, had, end of the sentence, dot. So brown foxes jumped over the fence. So we start doing feature engineering. Now, feature engineering is very important for any kind of machine learning task. NLP is not an exception when we apply machine learning to NLP. So let's do this feature engineering, starting with word-based features. So let's look up, let's take the word brown, which is at position number, no, foxes, which is at position number 2. 0 is hat, brown is 1, foxes is 2. So F21, feature number 1 for the second position. Dictionary index of the current word, foxes, which is an integer. Okay, so we have the alphabetically ordered list of the words, and the position where foxes appears, I take that position as a feature. By some reason, okay, I just decide I'll take this. F22 of the previous word, the same feature of the previous word, at which position does brown appear? And take that integer as a feature. And F23, the same feature of the next word, the position of the next word in the dictionary. So I have got 3 integers. Okay, 3 integers, which are based on the property of foxes, which is word-based feature. Then we take the part of speech tag-based feature, F24, the index of the part of speech of previous word. So the previous word is brown. And assuming that brown has been already part of speech tag, and assuming that it is correct, I'll take the feature as JJ, which is adjective. So the part of speech tag of the previous word is taken as a feature. This we call F24. Okay. So in part of speech tagging, the previous part of speech tag plays a very important role in deciding the part of speech. So that would be the part of speech tag based feature. Then we have morphology based features, okay, which is very, very important in discriminative model. F25, the fifth feature of the second word, foxes. Does the current word foxes have a noun suffix? For example, S, ES, IES, etc. So this is 1 or 0. So it's a Boolean variable, okay, Boolean feature, 1 or 0. It has a noun suffix. Of course, you can come back and say that how do you know that S is a noun feature? S can be verb feature also, runs, for example. Right? So yeah, that problem is there. So there is disambiguation needed at every level. Similarly, IES, ES, they can have verb features also. F26, does the current word have a verbal suffix like D, ED, etc.? In this case, this word doesn't have the verbal suffix, which is ed, so it is 0. F27 and 28 for brown, like for foxes. So we get these morphological features of the previous word also. And F29 and F210 for jump, like foxes. Here, F210 is 1. Okay, so jump has ed as suffix. So we're doing detailed feature engineering. What else? These features are opaquely represented in the word vectors created from huge corpora. Now, this painstaking feature engineering, you can avoid to a large extent if you work with what is called word vectors or word embedding. Okay, they capture many of these features implicitly in the word vector itself. Word vectors are vectors of numbers representing words, and it is not possible to tell which component in the word vector does what. On the other hand, if we do this kind of human engineered feature extraction, then the feature vector has a meaning associated with every component. This is a morphological feature, this is a lexical feature, this is a semantic feature, and so on. Okay, so now we come to the modeling equation. This is exactly what you will have to do for your assignment. Okay, for the second part of the part of speech tagging assignment. The second part is conditional random field based part of speech tagging. So conditional random field is a tool for discriminative modeling. Okay, and conditional random field is completely dependent on informative features. If the features are clear, good, complete, then these features are useful for doing the modeling and disambiguation. Okay, so now let's look at the modeling here. We have to propose an exponential distribution. In conditional random field also, exponential distribution is used. So you see here, so the word sequence is hat, W0, W1, Wn, and then dot. Okay. And the required tag sequence is hat T0, T1 up to Tn and a dot. This is what is desired. So probability of T is probability of T given W is I equal to W has to be there. I is equal to 0 to n plus 1 probability of Ti given Fi. Tag at position number I, condition on feature at position number I. And by feature, we have already seen what is meant. So the probability that Ti, the tag at ith position is T, okay, one of the tags from the repository, noun, adjective, verb, adverb, and so on. Given that the features Fi is modeled as an exponential distribution. Okay, it will be e to the power j equal to 1 to k lambda j f ij divided by a normalizing factor. Okay, so what is this? This is the probability that at ith position we have the tag p, okay, as a function of various features that we have got at position number I. That makes sense, okay? If at position number I have a word which is ending in the suffix ed, I can say that with high probability the word is going to be a verb. Okay, so this is the intuition. And the modeling of the probability, the modeling of the phenomenon is given by this equation. So what are lambdas? Lambdas are various, the weights of various features. Now, if I see a suffix ed, and if everything is absolutely fine, everything is in order, then ed is the shear such signal that the word is a verb. So ed has to have very high weightage there. Okay, so the features have to have different weights, and these weights are learned from the training data. So when in your assignment, when you are doing implementing the order switch dagger using conditional random field, you will have to do feature engineering and decide on their weights from the data. So there is an algorithm for conditional random field for obtaining these weight values from the data, which we will describe going forward. So conditional random field is a very powerful discriminative modeling framework, which was upstaged only by the arrival of neural network. Okay, so we have seen how rule-based NLP got replaced by data-centric NLP. In data-centric NLP, the heart of the operation was feature engineering, the kind of feature engineering I was describing. Then came neural network-based systems, huge amount of data. Do not worry about any of these fine tasks, feature engineering and so on. Create end-to-end the raw data and get decision. Okay, but for low resource NLP, languages which do not have huge amount of data, we have to make use of rules, we have to make use of feature engineering, statistical techniques, and so on. Okay? So you cannot say that, after 50 years, I will get millions and millions of corpus for Tulu language, or let's say there is a language called, I think, Kinoa in Africa. After 50 years, we'll get millions and millions of corpus, and then we'll think about NLP of those languages. No. People of those languages want the blessings of NLP. They want the fruits of language technology. So you'll have to make use of rule-based and statistical systems, create NLP systems, generate more data, synthesize more data, enter what is called a virtuous cycle. Okay, suppose you're creating part of speech tagging for, let's say, Manipuri or Boro or Tulu, those languages where the electronic resource is in small amount. So there we'll have some hand annotated data, create a part-of-speech tagger, which is not very accurate. Obtain the part-of-speech tag, do hand correction, manual correction, feed it into the data. Okay, so that increases the annotated data, create the model once again, train the model once again. Now the accuracy will be higher. So enter this cycle, a virtuous cycle, which will gradually create the part-of-speech tagger. So for all this, it is required to have good insight into language, linguistics, and properties, and then go ahead with the creation of the system. Now, I want to show you something interesting. Okay, so this statistics was collected some time back. All of you had filled a Google form, right? And from that, we could do some interesting analytics on this. Okay, so the TA team did this analysis. And what is interesting is that okay, we got about 300 responses, and 204 students are comfortable with Python programming. Okay, so which is fine. Uh, we can give good assignments in the class. 70 students are C, C++ savvy. 10 know both Python and Java. Both Python and Java. Yeah, and no. 10 know Python and C, C++. And this is the distribution of Java. So how many people know Python, C++, and Java? 3. Yeah. Yeah, that's okay, but maybe not everybody responded. But more interesting things are coming. Okay. Students by their departments, okay, mostly CS. Distribution of students who did courses under the AI basket. By AI basket, we mean computer vision, speech processing, machine learning course, basic AI course, and so on. So we find that about 79.4% of the class did AI course before, which is very nice. Okay. Very encouraging situation that way. The summary of expectations of students from the course. This part is most interesting. Okay, so GPT-4o gave this summary. You recall we asked the question, what do you want to learn from the course? And the processing was not done by human beings, but by the large language model, GPT-4o. So core concepts and fundamentals people wanted to know, and then there are subcategories. Advanced topics they wanted to know, practical applications, research and development, specific interest and overall expectations. And ChatGPT also gave details under each of these topics. For example, under core concepts and fundamentals, introduction to NLP, under key concepts, basic mathematical foundations and statistical methods underlying NLP, understanding classical NLP techniques like tokenization, part-of-speech tagging, and name recognition. This kind of hierarchical reporting was done by ChatGPT based on your response. Okay, but what is more interesting is this distribution of categories. This was done by another large language model, which is Claude. Okay, you see, fundamentals of NLP, 30% of the class is interested in this. Not bad, quite encouraging for the teacher. Then practical applications and projects, 20% of the class. Nice. Advanced NLP techniques and research, 15% of the class. Language models and LLMs, 10% of the class. That is surprising. Only 10% of the class. Okay, which means there is a lot of conscientiousness in the class. You are not swayed by the recent waves. Looks like 30% of the class would first like to know fundamentals and then move to LLMs, which is not bad. Okay. Then speech recognition process and processing, 8%. There is an NLP class, but of course there is a speech element. But I understand there is another course on ASR, which will happen next semester. Then machine learning and AI in NLP, 7% of the class. Some responses focused on the interaction of NLP with broader ML and AI concepts. Linguistics and language theory, 5% of the class you wanted to know. Okay, which is a small number, but of course the foundations, fundamentals, you have to take note of linguistic concepts. Okay, but this is a good picture for me. 30% fundamentals, 20% practical applications, 15% advanced NLP. So 65% wants to know substantial things. Okay, and done by large language models. The first summary or hierarchical summary was done by GPT-4o, and distribution was found by Claude, another. Okay. So this this particular formula is also called maximum entropy Markov model. Okay, pre-deep learning days, pre-neural network, maximum entropy Markov model, conditional random field, they were the ruling paradigm for NLP. So, and everything was founded on exponential distribution. Okay, the exponential distribution where the features were aggregated as sigma lambda into f. Okay, some lambda k into fk, each feature being given a particular weight. So for finding the weights, you will be able to appreciate the intuition. So in the corpus, if you find that words ending with ly, all the time get the part-of-speech tag of RB. RB is adverb. Okay, then surely Lee has very strong correlation with adverb as part-of-speech tag. So Lee as a suffix will get high weightage when it comes to deciding in favor of adverb. That is the intuition. Okay, so is there an algorithm to capture that intuition? That algorithm is there. That algorithm is a neural network. Okay, or there is this LBGF algorithm, which is a gradient descent algorithm, iterative gradient descent algorithm, but the idea is same. Backpropagation, LBGF, all of them are based on gradient descent. So we'll discuss this going forward. So the whole point is that there is something called an error function, which in trying to reduce that, you fix the weightages of the features. And when the weightages of the features are fixed very well, the error function on the data becomes very low. Now, error function on the data is typically captured by cross entropy laws. Cross entropy laws becoming smaller and smaller corresponds to maximizing the likelihood of the observation. Okay, so if we set the weight values properly collected from the data, then in future, when I see a word ending with Lee, I am very likely to tag these as adverb. Note that I am always using the word likely. Okay, the word likely comes because in NLP, we have to necessarily live with ambiguity. Words have multiple meanings, sentences have multiple meanings. So we have to disambiguate them, and that requires probability. So I suppose the intuition of fixing the weights corresponding to features is communicated to you. Okay, think about this. And the fixing the weights of the features are necessarily, almost always, some kind of iterative optimization based on gradient descent, most of the time. Okay, so that's it. So this is the modeling equation, and without going into a lot of details at this point, there is an exponential distribution which is proposed to model the situation. So then we apply the beam search algorithm. Why beam search? Okay, why beam search? We are interested in this probability. Okay, the probability where the product of probability of Ti given Fi needs to be computed. Now, at each position, you can have a k number of tags, let's say, at each position, multiple tags. So this becomes, therefore, an exponential search. At every position, you have k tags. So k to the power n will be the possibilities, will be the set of possibilities, no different from generative modeling. Only thing is that here, the search is based on features. Earlier, the search was based on transition probabilities and observation probabilities. Here, the search is based on features. So if the search is based on, if there is search, and if it is a sequence to be produced, the search algorithm necessarily has to be Viterbi or beam. Okay, a fundamental point about machine learning. The searching for finding the most probable sequence is either Viterbi based or beam search based. So let's look at beam search now. Again, we illustrate this with our running example. The brown foxes jump. The brown foxes jump with a hat and dot. So let's see. Let's assume the following tags for the purpose of discussion. D is determiner, like the. A is adjective, like brown. N is noun, like foxes and fence. V is verb, like jump. Okay, a very simplified situation where we have only these 4 tags. Now, what will be the tag, actual tag sequence for this sentence? The brown foxes jump. What is the tag sequence you'll get? The will be D. Brown will be A, adjective. Foxes will be noun, N. Jump will be V. So the tag sequence will be D, A, N, V. That should be the highest probability tag sequence. Okay, how does beam search proceed? Step 1. At the brown foxes jump. The word the is encountered. First, there are 4 next states possible. Assume that we do not a priori apply the knowledge that the can have only one tag. So there are 4 possible paths starting with hat, partial paths. Hat D, hat A, hat N, hat B. 4 paths, P1, P2, P3, P4. Okay. Then we have to commit to what is called beam width. Beam width is an integer which denotes how many of the possibilities should be kept open. Okay. Let the beam width be 2. How this is a hyperparameter. Okay, it's a design parameter. How have I come to the number 2? Just arbitrarily for now. But actually, a lot of linguistic insight and computational insight goes into deciding the beam width. This means that out of all the paths obtained so far, we retain only the top 2 in terms of their probability scores. Notice the difference with Viterbi. In Viterbi, there is no approximation. Okay, after you have made the Markov independence assumption, there is no approximation. You retain only the maximum probability partial path, drop all the other paths. Okay, after Markov independence assumption, there is no more approximation. No more approximation. But here, out of all the 4 paths, I retain the top 2 partial paths, which have the highest probability. Okay, so the question will be why? I mean, it is possible that what you dropped would have led to the best possible part-to-speech tag sequence. We say that we live with this imperfection. Okay, if our probability values are good, estimated from the data, and exponential maximum entropy Markov model or conditional random field, is a powerful algorithm, then we'll most likely get uh, accurate paths most of the time. Okay, so I retain the top two paths. We'll assume that the actual linguistically viable subsequence appears amongst the top two choices. So this is for the purpose of explanation and illustration. We are saying that our probability values are so good that linguistically correct partial paths come to the top, suppose. So the I is the determiner, and we get the two highest probability paths for the as P1 and P3. What is P1 and P3? P1 is hat D and P3 is hat now. In the last class, we understood that the can be a noun also. In the sentence, the is an article. Here, the is noun. Okay. So please begin thinking while the discussion is going on. Please keep thinking, how will the probability of this partial path be computed? Note the exponential distribution. Note probability of Ti given Fi. So what is the meaning of the probability of the partial path? It is product of those probabilities. Okay, product of those probabilities. And those probabilities, how can we know them? We can know them from this formula. In this formula, F's are known. F's are known because of what is called feature engineering. Either presence, absence, which means 1 or 0. Does it have a Li suffix 1? No Li suffix 0. Or they have integer values. Okay. How many morphemes are there in this string? In quickly, quick, and Li, 2 morphemes are there. So this kind of question. So F's are known. Lambdas are known from the data through gradient descent. So everything is known here. Okay. So from these, I should be able to compute the path probability of P1 and P2 and P3, P4 very easily as the product of dot to D. Okay. Then there is a data. Okay. So we get P1, P3. So we get dot D and dot N as 2 partial paths. So again, there are 4 possible tags. The next word is brown. 4 possible tags are D, A, N, V. So my partial path will be hat D, D, hat D, A, hat D, N, hat D, V. These paths are called P11, P12, P13, P14. Okay. The 1 indicates the path from the previous up to the previous word. And then we have hat ND, hat NA, hat NN, hat NV, P31, 32, 33, 34. Okay. So now we have got how many? 8 paths. Out of 8, since we had committed to beam width of 2, only 2 will be retained. 2 paths which have the highest probability. So again, we have to assume we do not have actual data with us. We are not computing this. From the data, you should be able to compute it when you have the CRF algorithm. CRF will have to make use of beam search, exactly like this in your assignment. So keep 2 or Viterbi also. So keep 2 possibilities corresponding to correct or almost correct subsequences. Brown is an adjective, but it can be noun also. For example, the brown of the eyes. There it is now. So we retain these 2 partial paths, hat DA, hat DN. Okay. So you might think that, okay, looks like there is some cheating going on now. We always have linguistically correct paths. Okay. So I'm assuming that our probability values are so representative of reality that these beams are being retained. These possibilities are being retained. Okay. So do not be confused. How come I'm always keeping the correct path or the almost correct path at the top? This is totally guided by the probability plan. So P12 and P13 are retained. What is the next step? Now the word encounter is foxes. It can be both noun and verb. Verb, he was foxed by their guide. He was foxed by their guide means He was deceived by the tricks. From P12 and P13, we'll get 8 paths, but retain only 2 as per the beam width. Again, there will be 8 paths. We assume only the paths coming from P12 survive with A and N extending the paths. So DAA, this is the wrong path, and DAN, which will likely be the winner going forward. Okay, so we have got the brown foxes, which is determiner, adjective, and noun. Now comes the last word, jumped. Last word, but not the last token. Last token is dot. Can be both a past participle adjective, the halted train, for example, and a verb. So it can be both adjective and verb. So again, DANA, DANV, these two paths are filtered out, filtered in, and retained. And then step 5, step 6 is the final step. On encountering dot, the beam search stops. We assume we get the correct path probabilistically in the beam. The beam width is 2. Okay, so very simple algorithm. Beam search algorithm is very simple conceptually. But the whole thing is controlled by probability, and the probability in turn is controlled by the data, the amount of data and the quality of the data. So you see the importance of data there. Okay. Now the question is how to fix the beam width. English part-of-speech tagging with pen, POS tag set, approximately 40 tags are there. Find categories like NNS for plural, NNP for proper noun, VAUX for auxiliary verb, VBD for past tense verb, and so on. There are very fine categories. We're going to look at that slide very soon. A word can have on an average, at most 3 part-of-speech recorded in the dictionary. This is also an observation from the dictionary. If you look at a good dictionary like Oxford Dictionary or Longman Dictionary, you'll see that there are at most 3 tags, okay, for English words on an average. Of course, the word above can be in all major parts of speech. Above is noun, verb, adjective, adverb, preposition, everything, all the time. Okay. So allow for 4 final category part of speech under each category, and with support from lexicon that records the broad category part of speech. So this is the method of thinking which goes on. When you are doing your assignment, you'll have to fix the beam width. How will you do it? Okay, we'll do it from these considerations. The average number of POS tags per word, and the final category POS tags, which is there in the pen text. Okay. Now, we have been talking about pen tag set quite a lot. So there are some 40 tags, 21 are shown here. So here, these tags you probably have already started looking at, but this document, which is there on the web, explains the tags with example. So CC is called the coordinating conjunction, and or. For example, both Delhi and Mumbai. So, and what is the part of speech tag of and? And will be CC, coordinating conjunction. CD is the cardinal number. So I had 5 mangoes. What is the part of speech tag for 5? 5 is called cardinal. It is the label is CD. DT is determiner. We have already seen. EX is existential there. So on the aside, as a kind of digression, English sentences can never be without a subject. A subject has to be there. So there is this existential there. There was a king. So there are jokes on English language. Like when you say there was a king, then somebody would ask where. When you say, so this there is called semantically vacant. Semantically vacant. This there has no semantic role. It is just a syntactic subject for the sentence. There is another funny construct in English language. That is it. It is raining. So English is Hindi is barish ho rahi hai. Now what is it doing that? It is raining. Okay, that is because you need a subject. So it and there, they have these two fun roles. They are semantically, syntactically full. Let's say. Then in is preposition. So with, out, in, etc. I call in. JJ is adjective. JJ is adjective, comparative adjective. Oh, we are not able to see this. How come? Yeah. So what I said was CC is the tag for and, CD is for numbers, EX is existential, there was a king, and so on. LS, what about LS? Least item marker. So a text is a text. So many times you have a list. One, let's say grocery. Two, travel. Three, something else, and so on. So what do these numbers, 1, 2, 3 get? They don't get CD, cardinal. They get a tag of LS, the list elements. Okay. Then MD is modal. I can go. What is the part of speech of can? I could have gone. What is the part of speech of could? Okay, all this is plural noun. NNP is proper noun. NNPA is proper noun in plural. Proper noun in plural, like Americas, for example, and so on. So study these part of speech tag document carefully and understand their role. Then only you will be able to do a good error analysis of the output that you get from your system. Maybe the accuracy you're getting is only 30%, where part of speech tag accuracy should be at least 90 for downstream NLP application. If you're getting only 30, then you have to go and do an incisive error analysis. That will require understanding the tags completely. Okay, so find the